to John.
Thanks very much, Oz, and then also obviously to the entire ONF community. And so great presentations by Larry and Alex. So let me bring up my slides as well here. So I'm going to be talking today about deploying 5G faster with DRAN. So when we kind of take a look at the 5G system and the overall impact of 5G, I think we're already seeing today in these deployments this huge expanse, whether it's public wide area networks, private networks, things like massive IoT, deploying 5G in, say, factories, or the role it has in smart transportation. Another interesting aspect, 5G not only about fixed wireless access and mobile, but then also the evolution of new types of compute form factors. So whether it's evolution of PCs, evolution of devices, and at the same time, the role of wide area fixed wireless connectivity. When we kind of take a step back and say, well, where are we at in a numeric standpoint in terms of the deployment? So as a snapshot today, 80 plus operators with 5G have already commercially deployed, and 385 plus operators are investing in 5G globally. If we look at smartphone shipments in expectations for 2020, that's 200 million devices. And in terms of 5G smartphones to ship in 2022, 750 million. And so this results in 1 billion plus 5G connections by 2023, 2 years faster than 4G. And so it's one of the things that when we say, well, what is enabling 5G deployments to happen faster? What is enabling the entire global ecosystem to pivot into these 5G opportunities? And obviously, disaggregated RAN is one of those core technology enablers. The transformation of where networks were in the 3G to 4G era versus now the 4G to 5G era, we're seeing obviously a much larger number of different types of topologies, different types of network deployments. And obviously one of the reasons these investments are being made globally is because of this interest in new use cases. If we want to take a look at the standardization timeline, so I'm holding in my hand a 5G release 15, that is the first specification of 5G in our device. So it has sub-6, it has millimeter wave, so there's a huge amount of content in that very first release of 5G, namely 3GPP release 15. And now we've also already completed release 16, which helped that expansion. In release 16, we added ultra reliable low latency communication and also things like time sensitive networking for industrial IoT, or even taking things like enhanced 5G V2X. So that is vehicle to anything side link, where it's not only vehicle to vehicle, but also vehicle to roadside units. And in release 16, 5G was also expanded from deployments in licensed spectrum to enable deployments in unlicensed spectrum. This is called 5G NRU, and this can happen even if you do not have any licensed spectrum. So it can be a standalone 5G unlicensed spectrum deployment. We also took technologies like EMTC NB-IoT, the low power wide area, connecting those to the 5G core. And in another aspect is the role of positioning. If we look longer term at interesting 5G use cases, not only obviously is downlink and uplink speeds, data rates, coverage important, but the role of positioning is also very interesting for many of these new applications, whether it's augmented reality, where we want to know where the user is situated in order to place information on their head-mounted screen. At the same time, we're also seeing interesting applications relating to, say, factory AGVs. And so when we look at release 17 plus, a lot of other longer term concepts related to even lower complexity, things like higher precision positioning, kind of taking 5G into that next evolution of deployments. And so this is, we now have just begun on the global standardization of release 17, and at the same time, the research targeting release 18, 19, 20, and onwards into 6G is already happening. If we wanted to say, well, what is the technology and the economic opportunity? So we commissioned an independent economic study to understand, well, what is the economic value across these different markets? And this is where we're seeing the aspect of $13.2 trillion. And this spans a wide range of use cases, whether it's precision agriculture or construction and mining, digitized education. Here we're seeing the importance of connecting people not only within the classroom, but also beyond the walls of the classroom. And even things like connected healthcare in terms of patient monitoring and also the role of sensors, the role of having the right data at the right place at the right time. And a lot of this also transforms into richer mobile experiences. I mentioned earlier smart manufacturing as a good example where the evolution of 5G is really well aligned with a lot of the challenges to connecting a factory setup, and even things like intelligent retail and logistics. So there's one of the reasons that this overall global ecosystem has been focused on 5G is because of this wide range of use cases beyond consumer mobile broadband. And at the same time, these investments are being enabled to be more cost effectively deployed because of things like virtualization and disaggregated RAN. If we want to take a specific look at the factory setting I mentioned, what's interesting there, when we originally were designing 5G and beginning that kind of global standardization discussions in terms of the specific timeline, that was kind of the 2014, 2015 era. And at the same time, people were saying, well, there's going to be three core use cases: mobile broadband, massive IoT, and ultra reliable low latency communication. But the interesting thing is, well, how could we design a 5G system that was going to support all of these use cases efficiently? And that's because the reality is, in certain settings, you're going to have literally all of these devices and use cases that QoS needs simultaneously. So the desire and the need to efficiently support these services, where there are different numbers of whether it's latency, data rate, availability. So considering things like a security camera, a head-mounted display, or a handheld terminal, these have different requirements compared to say an AGV or a sensor that's giving data very infrequently. And it's when you look at the role of edge computing and analytics, and obviously, I think as many people participating in today's discussion understand, it's about where the computing is occurring, where the communications is occurring, and where the control is occurring. So this kind of evolution of cloud and edge cloud and device and the processing relative to the services, that's all kind of intersecting in these 5G technology discussions. I mentioned the V2X, and one of the things I just want to kind of highlight to the audience is this aspect of where is the overall transportation fabric going. So not only can we have enhanced network communication, but also direct communication. So as part of 5G, not only are we designing signals for devices to communicate with base stations, we also have things like base stations being able to communicate directly with each other in something called integrated access and backhaul. But what's also very interesting is devices being able to communicate directly with each other on a side link channel. And so that enables things like V2V, so vehicle to vehicle, or vehicle to infrastructure, where it could be a roadside units, or even evolving into things like vehicle to pedestrian, where the device, whether it's a person is holding their handheld device, communicating directly with vehicles. And so a lot of different interesting applications that are latency sensitive, and then also things related to, say, safety and collision avoidance. And then the other thing is the massive Internet of Things. So IoT obviously has been a term in our industry for many years. And at the same time, it's continuing to have this evolution of, well, where do we want to have wide area connectivity? Where do we want these devices to be able to have incredibly long battery life? Because it's not a consumer device that's getting charged every day. It's something that's being deployed in a field, something being deployed in a more of a sensor era. So it's just an interesting aspect of, as 5G is being designed, not only for all of the kind of consumer-oriented services, it's also something that's making its way significantly into examples like factories and V2X. When we look at then the 5G network, so I don't really, obviously for this audience, need to describe all of this, but the reality is we are undergoing a huge transformation in what is happening on the network side. So this movement from traditional RAN, obviously, to things like a centralized RAN, and then into virtual RAN and mobile edge compute. And so one thing I just want to highlight is that aspect of the compute side, about what is happening and where it's happening. So the role of edge compute is incredibly important because it also then relates to the latency. So when services are being offered and when things are being deployed at the edge of the network versus in the deep cloud, it changes the notion of what is on premises. It changes the notion of, where is the, as we're talking about across all of these discussions today, the notion of the functional split and the role of disaggregation. And so just that aspect of the edge compute intersecting then with how we're doing the communications across the RAN. So let's look at some interesting examples where not only disaggregated RAN hardware and software with white box implementations. So whether that's virtualizing the core, virtualizing a BBU, and then obviously having more COTS compute in terms of off-the-shelf performance and cost structures. And then opening front haul and back haul interfaces. And then disaggregating layers of the protocol stack. And so this is another aspect where enabling this across the protocol stack, disaggregation and control plane and user plane also both playing a part. And we look at, well, why are we doing this? What are the benefits of this disaggregation? Well, one of the very interesting ones is supporting different deployment scenarios and also having a higher utilization of scalable resources. And this is also going to be something that's core to efficiently deploying new services. So when we looked at the 5G vision of all the different services we wanted to support, it's obviously not just about getting macro cells out into a network with more centralized baseband. It's actually about how does the system overall adapt? What are the different ways things can be configured and that the hardware and software can come together to enable this efficient deployment of new services? There's also real estate savings and the ability to build the RAN itself more cost effectively. And so when we look at these, kind of going into that next level of detail, placing the processing and the analytics where it is simply most needed, and looking at things like resource pooling. And so what is the best way to have these trunking gains? And supporting lower end-to-end latency. So when you look at the 5G use cases, one of the most important parts then is not only the data rate needs, but the latency needs. So the responsiveness of the network and the responsiveness of the overall end-to-end performance becomes core to that value proposition. And so what can we do in terms of tailoring the dimensioning and the features to suit the specific use cases in a 5G private network? And then also reducing the cell site footprint. That's obviously important for many types of enterprise deployments. Or even looking at the overall ecosystem of and the number of vendors actively participating. So then moving on into this aspect of the deeper technical details into the RAN. So I think everyone here is probably familiar with the notion of option 7, option 2, and the trade-offs in the different sorts of splits. And it's something where when we look at the virtualizing the central unit relative to the distributed unit and the radio unit, we see then specific opportunities. And this aspect of, what are the pros and cons of option 2 in terms of real-time intelligence for machine learning or relaxed backhaul requirements? How can we have the access point with the scheduler? And so when we look at the role of these use cases that I've discussed earlier, and then how does this interplay with the different options? One of the interesting things then is what is the use case we are trying to achieve? So when you look at a distributed unit and things like coordinated multipoint, so technologies like MIMO that have obviously been on the R&D stage and are now part of commercial networks, well, what is the evolution of something like multiple antenna processing for reliability, but in a way that we're literally having a significant increase in the computational requirements to solve for those RAN deployment scenarios. So this real-time intelligence and the role of machine learning, when we look longer term at data-driven network design, data-driven wireless design overall from a system standpoint, then all of a sudden where the machine learning is occurring, what is the machine learning that's on device, what is the machine learning at the edge of the network versus what is the machine learning in the cloud. So this relates to, where is the offline training versus say the real-time decision making. And so when we look overall at the aspect of compute and the aspect of control, then this is where these specific designs are obviously very sophisticated as we're trying to get the right decision for the right particular deployment. Then when you look at then the industry and enterprise example, so this is where, getting into that next level of detail on the edge compute aspect. So the 5G public network in relation to the 5G private network, and then the role of the edge cloud in regards to the role of the central cloud. So if we look then at this end-to-end opportunity of how we're able to say reduce latency or support multiple services, or even increase data security and privacy where data is being kept local and physically secure. So these all work together to increase this scalability and then also availability. So the role of, in our view, vRAN and mobile edge compute, they go hand in hand to transform some of these particular industrial opportunities for 5G. And then when we looked at Qualcomm's role, we're obviously incredibly active in the aspect of this disaggregated RAN and ensuring solutions can come to market effectively. And so we have the FSM 5G RAN technology, where it's a complete modem to RF solution for flexible, scalable, and cost-effective deployments. And this also is something that enables enterprise-grade indoor and outdoor performance. And it's obviously a wide number of global infrastructure innovators are working with Qualcomm. So thank you very much for this participation. And Oguz, I really look forward to the Q&A.
Thank you, John, for the